Hi everyone. How are we all doing? It's another Tuesday, and I hope we're feeling great. I hope that the weather is not affecting our mood and productivity today because over here it rained earlier and it's been quite cold and I don't know, I've been feeling lazy all day. But yeah, I hope your weather is not like mine from Lagos, Nigeria. And I welcome everybody to today's PPL session. Last week we treated Python visualization, where you get to get insights from data in visual form. This week is all about statistics with Python, and I hope you're excited for what today has to offer. My name is Alima. I'm your host as usual, and I have with me Alfred Tuva, who is your technical mentor, who is going to take you through today's session on Python with statistics. So get your pen and papers ready, or your, I don't know, is it your AI notebooks or something? And yeah, and come prepared. Okay, so before we dive in, let's just go over the rules of engagement. If you have any questions, as usual, put them in the Q&A so that they'll be attended to, so that they don't get lost in the chat. Feel free to use the chat, but please use it respectfully and liberally. Let's respect ourselves, and let's be let's just comport ourselves. Also, this session is for you to learn the learning content for this week, so that you get to attempt the assessment for this week as well. So come listen, learn, and engage, and tell others to come and join as well. This session is on. Tell others, your friends, your squad mates, your peers, tell them to join our live, and the session is starting already. So I'm going to hand over to Alfred now, who is going to take you through today's session. All right, Alfred, over to you.
Thank you, Halima. Hi, everyone. Welcome to today's session. I hope you're excited. It's been a minute since we've had a session together. I know you've been learning a lot over the last couple of weeks, and it's my hope that you're excited to learn something new again today. So today we'll be looking at statistics, and I think this is one very, very, very broad field. I think I'll just start out by saying that it's a very, very broad field. I don't think the 2 hours we have today is enough to cover absolutely everything. But we're going to have a session where we get to see what statistics could be used for, how it fits in our day-to-day as data scientists. So just give me a second to set up and we will get started. So the World Cup is it starting this week? How many of us are excited about the World Cup? Anyone? How many of us and which teams are you guys supporting for the World Cup? You can drop that in the chat as I finish up here. Do you think Cristiano is finally going to win the World Cup, or is it a lost cause for him? Did Messi finally beat Cristiano? I think that's one of the battles we're looking forward to this World Cup. Anyone? Wait, you guys don't watch football at all? That's disappointing. All African teams from Shegun. Okay. Okay. So I was asking the question about the World Cup because for today's session, I've decided that we're going to actually use the World Cup to try and go over it. Someone says they're supporting South Africa but want Ronaldo to win. I'm not a hater, but I don't think Ronaldo is going to win this World Cup. Let's wait and see. We'll be back here. I think you guys will be done with this program with Python by the time the World Cup ends. But I don't know, maybe after the World Cup, it would have been really cool if we could do something with the data from this year's World Cup. But for today, we're going to be spending time with data from the World Cup, and that's from the last, how many years? I don't know how many years the World Cup has been running. 1930 to 2002 to 2022, and that's around 800 matches, 92 years of football. So why are we here? Let's talk about that first. And I think it's one of the things let's talk about in the resources that have been shared this week, the data science process. There is certain steps that are going to be taken for every data science project. The first one is you collect the data, from various sources, you get data and you use it. The second step is to clean the data because data might come with some things that you do not need. It might be missing some things. You might need to change a few things here and there. You clean your data. Then the next step is the explore phase. And this is where you now start to explore the existing data. After you've explored the data, you then move to building models using the data, which I think, if I'm not mistaken, someone correct me, is probably the next phase of your learning journey. And then finally deploying the data and using it to do something. So a hypothetical example of the data that we're working with today, the World Cup, maybe someone would want to build a prediction model of some kind. But I would say right now, right here, small issue, a small blocker with football data is, I think it's probably very, very hard to predict because, so for instance, if you're working with World Cup data, uh, there's a lot of variables. The World Cup is played every 4 years. So within those 4 years, we don't have any data to see how has South Africa been playing for the last 4 years. Have they been good? Maybe France won the last one, not France, Argentina. That's how I wanted France to win the last World Cup. So yeah, Argentina. Unfortunately, Argentina won the last World Cup. But between 2022 and today, have they been playing really, really well? Do we expect them to still win? See, there is this huge gap. 4 years where we don't have data that would actually affect this year's performance. So I'd say prediction on this, just using the World Cup data, might be a little bit hard. But a hypothetical example is after we've worked with this data, maybe you could build a prediction model, right? So yeah, good question from Shay. What's the likelihood of an African team winning the World Cup? Is this the year? Someone has been saying, this year the World Cup is in America. America is very, very hot right now. I think it's summer right now. Someone was saying maybe African players are going to be advantaged, but someone says, you know what? Okay, South American teams might also be advantaged because their countries are hot. So there's a lot of variables in play here. But anyways, let's just jump in and try to explore our data, look at a few things. Okay, so let's get started. First thing is you're going to need a couple of tools. So, and I think you've already interacted with some of these tools. Last week, I think you were learning about visualizations. Honestly, I didn't join that session, so I'm not sure what tools you covered, but there's several tools that we're going to be using. And I want to give a disclaimer right now. You'll see a lot of code today, a lot of tools. It does not mean that I, Alfred, know all these tools, know all these commands at my fingertips, that I can use them at will. I'm not that brilliant. If I'm being honest, I've actually spent the whole day today just preparing for this session. I do have some notes on a separate screen here. So do not feel intimidated by what we're doing. Just try to learn, try to ask questions, and we're going to learn together in the process. Okay? So let's get started. Okay, so we're going to start by importing some tools that we need. So the first one is going to be NumPy. And NumPy, this does a lot of the math that we'll be doing. We also need to import pandas. Pandas is going to be used for working with the tables, the data that we have. Excuse me. And then we also have does matplotlib. And this is going to, we are going to use this mostly for drawing our charts. We'll draw a couple of charts this session. And then finally, we're going to import stats. And this is going to provide us with some statistical formulas that we can use here. We're not going to be building out these functions from scratch for today's session. If you're curious about that, always say it's always a good way to learn, to try and build these things on your own. It's going to be a lot of hard work, but it's going to be an important learning process. So we've imported these libraries and they all play a different function. So the next thing we're going to do is we're going to fetch some data that we're going to be using. We're going to fetch some data set from GitHub, and I have the URL saved here. And I'll just paste that in here. So we have this URL, and if we just go look at it, I think this is going to probably try and download it as a CSV. It's a CSV, and it contains all World Cup matches for the last, was it 90 years? Yeah, 90 years of football. And we'll be using this session and some statistical skills. We'll be learning a few things to try and analyze this data, see if there's any insights we can get and get to learn in the process. Okay, so first thing is we need to load in this CSV into a table, right? And we already imported Panda for working with tables. So we're going to create a data frame and import this. So pd.read CSV, and we'll pass in the URL. So once we do this, it's going to fetch all of that data, run it, it's going to run, but we've not actually did call printed anything important. Let's see, can we? So since it's a CSV of matches, I wish you could download it and view it. Now let's just print the length of the matches. So we know it's several matches inside there, so we can just print the length of DF. I think that should give us something. Yep, and we get 964. So we have 964 World Cup matches in our data set. So next thing, let's just look at the structure of the data. And for that, we're going to use the head method. And if we do that, this is what our data looks like. So see, so in the year 1930, on 13th July, certain time, the first game was France versus Mexico. So the home team was France. They scored 4 goals. Mexico scored 1 goal. Yeah, we also get to see who the scorers were, the away scorers, whether there was any extra time, whether there was penalties, the stadium it was played in, location, and even attendance and the referee. So honestly, I'd say we've probably skipped one step because we've just imported the data and we're going to start using it. Because depending on the kind of work we're doing or the kind of projects that we're doing, there's probably some data that we wouldn't need here. So I want you guys to just let me know in the chat. So let's say we just want to analyze actual matches. What do you think are some of the columns we could get rid of? I think this would probably fall under data cleaning, right? So what do you think are some of the columns we'd probably get rid of? Or what is maybe a column that is missing that we could probably add? Anyone? You can just drop in the chat. What do you think are some of the columns that we could probably get rid of when we just want to analyze matches and their scores? Nice. We see there's this unnamed one here. Very good. From Bena. What else do you think we can get rid of if we just want to analyze matches and their scores? Anyone else? The referee. Do we need the referee really? No, we don't need the referee for this. Attendance, unless we want to play around with attendance to see what we could do. The stadiums, the locations. These are some columns that we probably wouldn't need. Even the scorers, who scored. This probably isn't data that we would want to use if we're just analyzing our matches. Okay. So the first thing that we need to talk about is the kind of data that we have here in our data set. And these are some of the data types that I mentioned in the resources also. So the first one we have is nominal data types. One example is like the home team, Brazil. And this is just a label that is used. You see, it's not a number, or we can't use it to do any comparison or anything like that. So this is a nominal data type, and an example is just the home team, Brazil. Then we have another data type, which is discrete, and this is going to be whole numbers, right? For example, the year 2002, or the home score. France scored 4 goals in 1930. So those 4 goals, that's discrete data. So discrete data is always whole numbers. You can't score 1.5 goals, right? So it's always going to be 4 goals, 1 goal, 0. Then the other one that we have is attendance, continuous. And continuous is data that, I think from the name, it's continuous. So for example, attendance for a match can be 80,000 for one match, another match is 85,000, and so on. And Why this matters is because the different operations that you're going to be performing when you're performing statistics on kind data on any data set depend on the data type. So for example, you can't calculate averages of team names, right? This is nominal data. You can't use it for any comparison. You can't rank it in any way. It's just labels. So yeah, four data types. Those are three. I think there's one more. I've forgotten it. It's just because it's not featured in our data set probably. Anyways, so still back to cleaning up our data. There is one more column that would probably be useful for us, and that is just the total goals that have been scored for every match, because right now our data set talks about home score, away score. And I think most of the analysis that we'll be doing is going to be actually on the total number of goals that have been scored inside for each match. So I'll come down here. And we're going to add another column, so df, and then let's call it total calls equals to df, and then we have home score plus df away score. So we're just creating a new column from the existing columns already. So we can do that, and then to just confirm, we can say again df dot head to see if we have this new column. So let's check. We can see we now have a new column, total goals. So this is the column that we'll probably be using for a lot of the analysis we'll do in today's session. Now, so I think we'll be approaching this from a question standpoint. So we have all this data, and maybe we just want to answer some questions. So first question we'd have is, what does a typical World Cup match look like? And we'll be focusing on the goals that are scored in the World Cup match. So we're going to, when we say a typical world match, this could be things like, on average, how many goals are scored, are, or how spread out are the results of the goals that we get for each match, and so on. And this is actually statistical data, and it's one of the first ones that we're going to be talking about. And there's three things we'll be looking at: mean, median, and standard deviation. So all of this is useful data, and it's usually, I think, one of the first things that you check for the dataset that you have. It's fairly simple to get this data. So, and we're going to start with simple examples even before we actually jump into our actual data set. So for our mean, I think we know mean is simply the average. Add up all values, divide by how many there are, and you get your value. But there is a small limitation with mean. And it's that extreme results are going to drag away from the truth. See? And we'll see what that means in a simple example right now. So let's assume we have maybe scores for 5 matches, and the scores are 1, 2, 3, 4, and 4. So we have 5 matches, and these are the scores for those 5 matches. Now, if you want to calculate the mean for this, we use np.mean. Let's pass in scores. Then we need to print that. I think we should have just printed it out. Print np mean scores. Look at that. So our mean in 5 matches is around 2.8. So this is the average goals. And if we look at our numbers, we have 1, 2, 3, 4, 4, 4. So the average seems okay, right? Okay, yeah, it looks okay. The distribution seems okay. So when someone says we had 5 matches, the average is 2.8, you'll naturally assume, okay, the goals were around that number, 2.8, so maybe 3, 4, 5, or 1, 2, 3, and so on. But the problem with mean is, what if in one match we get a team that scores 10 goals? What's going to happen? Look at that. The mean becomes 4. So you think, okay, does this mean that it was probably 3, 4, 5 goals? But no, and this is the point that we're saying. One extreme result is going to drag the results away from the truth. So one team or one match that had a result of 10 goals, it might give you a false conclusion because you see this mean and you assume 5 goals there, but you'll find that it's only one team that actually had 10, only one match that had 10 goals, and it sort of skews your results because you think the mean is probably true. So we do have a couple of other, let's call, we have, let me just say mean is, and then let me use some F strings so that unmatched. Did I forget to close something? Mean is, what's missing here? Print F. There it is. So the mean is 4.0. Now, another value we can look at is the median. And the median is simply the middle value when everything is sorted from lowest to highest. And the nice thing about this is that it ignores the extreme results. So same data that we have here, if you want to check out the median is, this is going to be NP dot median. Sorry, there should be brackets, NP dot median. Then we pass in our scores, close it up. Look at that. So despite us having one outlier, one match that is not, do we call it not normal? That's an extreme. It has 10 goals. We see that the median gives us 3. And honestly, it does feel like the median is telling a little bit more truth compared to mean when you're trying to assess this data. So if you want to maybe say, okay, people who are scoring around a certain number of goals, if you look at median, it's probably telling the truth more because just looking at this simple data, 3, and then you can think 1, 2, or 4, you just have one outlier, right? So when the result is extreme, the mean is going to lie and the median is what is going to tell you the truth. So that's one thing that I guess we do need to consider. So the other value we can look at is standard deviation. And we've said this is a measure of how spread out the results are. And why this is important is, let's see, we have maybe match 1, not match 1, let's call it group 1. I think every World Cup game starts with group stages, right? So group 1, the results of the match is something like this: 2, 2, 3, 2, 3. Then we have group 2. And again, for these ones, it's a little bit more spread out. So we have 2 groups and they all have different results. Now let's check what's going to be the mean of these 2 groups. I was trying to look for an example where we're going to get the same mean. Then let's change this to group 1. So the mean for group 1 is 2.4. Let's see, 8 plus 6, 14, 17, 18. Four, 7. Okay, so mean for group 1 is that. Let's try for group 2. The mean for group 2 is 3.6. Okay, so let's look at the standard deviation of these 2 groups now. So for standard deviation, just like the other one, This time around, we're going to say standard deviation is np dot std scores, not scores, one. For 2, should probably have limited these to, what is it called? Certain dot 2f. Yep. Let's just limit it to 2 decimals. So the standard deviation of group 1 is 0.49, while the standard deviation of group 2 is 3.01. I was trying to find an, let's see. Okay, I think for this we can say the mean, okay, it's not almost the same. This is vastly different, right? This is vastly different. But I think what we can showcase is how standard deviation is going to give you like an entirely different story. It shows us how spread out the results are, right? So for this first group where like the results are almost the same, the mean was 2.4. Let's see if we can switch up this example so that we have like something that's, this is 2 plus 2, that's 4, 4 plus 3, 7, 8, 9, 10, 11. That's 1, 3 plus 4. 11. Let's try this example. Mean is, okay. Yep, that's a better example, I think. So with this new example here, so group 1 is 2, 2, 3, 3, 2, 3. Group 2 is 0, 1, 2, 2, 8. Now, let's look at the stories that the mean is going to tell us and what the standard deviation is going to tell us. So if we look at the mean, we get an average of 2.4 for group 1 and 2.6 for group 2. So if we only decide to look at the mean, the most likely conclusion we could make is, okay, these matches seems to be easy. Goals were around 3 or 4, so you might think maybe team 1 had 2 goals, team 2 had 2 goals, or team 1 had 1 goal, or team 2 had 3 goals, and so on. But when we decide to look at standard deviation, we get to realize that it's actually different. Even though the mean is almost similar for these two groups, standard deviation of group 2 shows us that group 2 was, we could say, slightly more chaotic. There is a match that ended with 8 goals. So looking at the mean only, not enough. Because standard deviation is going to show us like a completely different spread. It shows us how spread out the results are. See, there is a team that a game that probably ended with 0 goals, but on the other end of this, on the other end of the spectrum, there's another team that ended with 8 goals. So if we decide to look at standard deviation, we get to draw different conclusions. Group 2 was probably a very chaotic group. The games were very difficult, probably even more entertaining, right? So imagine a game ending like 8 goals. That's probably definitely an entertaining game, unless the other team was not scoring anything. But so yeah, those are some of the first 3 concepts that are going to start us out as we move ahead in statistics, because they sort of power everything else. Yeah, so let's dive in and start now building means for our actual football matches, see what we can get for standard deviation, what the medians were, and so on. Okay. So we need to build the mean goals of our actual football matches now. So average number of goals across all World Cup matches. So we used small examples, but now we're not going to use the big examples. 900 matches, what was the average goals? What do you guys think? What could possibly be the average goals of all the 900 matches of the World Cup that have been played over the last 90 plus years? What do you think the average is? So to get the mean goals, so this is equals to df So we did have a column for total goals, right? So that's the one we want. And we want to get the mean for this column. And we can print average goals per match was, and that's going to be mean goals. I think we've already seen that our calculations sometimes give us very big decimals, so let's go with a small one. Let's limit it to 2 decimal places. And if we run this, and you get that the average goals per match for the 900 matches that have been played was 2.82 goals per match, which is, I guess it's interesting. For 900 matches, people were playing around 2, 3, 4, or 1 or 0 goals. I think it's something, if you've been watching the World Cup, it's also something that's slightly similar to what we've been seeing, right? Okay, we've seen the mean. Let's look at the median. Median goals equals to DF total goals, sorry, dot median. Forgot to print it out. So print median goals or median goals to F, and you get the median goals were at around 3. So this is going to mean that less than half of the matches that were played in the World Cup resulted in 3 goals or less. Because remember, we said the median is the midpoint. When we arrange all the total goals for every match, starting from the first match all the way to the last match, the median goal is going to be the midpoint of that arrangement. So median was 3 goals. Now let's look at standard deviation and see what that's going to look like. Standard deviation, STD goals equals to DF total goals dot STD. Let me just copy this. I don't want to keep on typing all that. STD goals were STD. And we get that the standard deviation was 1 point, forgotten 0.2, that we should be 0.2F also. The standard deviation was actually 1.93. Now, the conclusion here is that for the World Cup, for all the games that have been played starting from 1930 something to 2022, half of the World Cup matches ended with 3 or fewer goals. So it was either 0-3, 1-2, or what is it? Yeah, it's either 0-3 or 1-2. Am I missing another possible combination for all the goals? Because it can be 1.5, 1.5. So more than half the games, half the World Cup matches that have been played, they ended with either 0-3 or 1-2, because that's how it adds up to 3. So less 3 or fewer goals. And the typical results of the World Cup is between plus or minus 1.5 goals average. What do you mean by that? A typical result is within plus or minus. How do we put plus or minus? Plus or minus 1.9, because this is our standard deviation, right? So if you take the average was 2.82. So 2.82 plus 1.9 or 2.82 minus 1.9, that could be considered as the range for which most of the goals were expected. Okay. Okay. We can still do some more analysis. So let's look what is actually the highest stored, sorry, the highest number of goals that we had for the World Cup. And I think for that, that's going to be easy. So max goals equals to DF. Let's look. And this is going to help us build a bar graph, because I think not a bar graph, we're going to build a graph. And we want to see what is the maximum number of goals. And max goals. So the maximum goals that we've ever had in the 93 years of the World Cup was around 12 goals in a match. So we now want to try and build a bar chart that shows how goals have been distributed over the last several years. And it's just going to be the number of matches and how many goals were scored in that match, as simple as that. So we're going to build a graph. So first thing, let's define our canvas. Let's go with 10, 5. And then let us now plot this out. Total goals means how many column are we expecting? Since we've seen we had 12 maximum goals, I think we can go with 12. And then for colors, don't know, let's use green. Edge color goes to white for our graphs themselves. And then the width of the actual bar graph, let's go with 0.8 like that. Nope. What's happening? Very many errors. I keep on pressing Shift Enter instead of Enter. I'm so used to typing in places where we use Enter. Don't worry, we'll fix it because we were not even done. And then, wait, but what's this error? Let's check. Attributes error, hist df, total goals. We have beans. Did I forget to close something on X label is goals in the match. The Y label is going to be number of matches. And I think let's arrange. I want to display all the different goals. Plot.show. Yes, colors, or it should be color, not colors. Yep, should be color, not colors. Another one. And these are just my typos. X label. And there it is. And if you look at it now, so this is a histogram, right? This is a histogram that shows the number of goals in matches. So one goal, how many matches resulted in, now this is actually, I think this is 0. 0 goals, 75 matches. How many matches resulted in 1 goal? Around 170 something. How many matches resulted in 3 goals? 200 and something. How many matches resulted in around 4 goals, 200 plus, I think, and so on and so on. So this is a histogram. And yeah, it's a nice, we get to see like a nice distribution of the number of goals in the match against the total number of matches that were happened. Now, on this same histogram, could actually plot out a line to show us where the average is. So let plot.axv line. This is going to create a vertical line. And this vertical line is going to be based on mean goals. Let's change the color to give it a different color. Color red. And the label, we can give it a label also. Label equals to average. Let's just call it average. It's simple. And I think we just need to add a legend. And look at that. We get to see that the average was at this point. So this is the average. And you can see this distribution looks okay, right? Now, most matches landed in the 1 to 4 goals range. Very few were goalless, and very few were high-scoring thrillers, right? Matches that scored, what is it, around 11 goals. That's very few. Actually, we said the maximum was 12. The maximum was 12. It's a match that resulted in 12 goals. And you can see it's very, very few. We can't even tell the exact number here. So I think one thing that I'd want us to notice from this histogram, which is a distribution of goals versus the number of matches that resulted in said goals, is the shape of this. This shape is very, very important in statistics, and we are going to revisit it, okay? So far, we've done some like simple analysis on things like mean, average, and we've seen you can actually gain some like useful insights from it. See, if you have the mean and you have the standard deviation, you can probably approximate. You can say generally goals are around mean plus or minus the standard deviation. And you wouldn't be very, very off. You wouldn't be very, very wrong when you're trying to look at Twitter, when you're trying to analyze your data. So let's move on to another question. So if we decide to look at 2022, the World Cup where Argentina won, and we just want to analyze it. So far we've described or we've analyzed 92 years of football, right? And the assumption is, what if someone had to analyze only 1 year, 2022? Will it be like a fair representation of the whole World Cup, all the years that it has existed? No, that's something that we're curious about. Okay. And this introduces us to some ideas or concepts in statistics, and this is population and sample. So a population in our scenario is going to be every single match in the group that we care about. So if our data set is 800 plus matches, how many was it? 800 and something, I think, 800, which was actually 964. Yeah, I think it was 964 matches. So our data set is 964 matches. So we could say our population is 964 matches, if that's the entire data set that we are interested in. A sample is a smaller piece of the population. So let's say we want to analyze a smaller piece of that, and that would be maybe like 2022 data only. Okay. So we want to analyze 2022 data only, and that's a sample of the entire population. So we now just want to look at how does this sample compare to the full picture, and why is that an important concept? Well, the thing is, in the real world, most of the time, it's not possible for you to have the full population, to perform analysis on it, and so on. An example that I talk about here is a doctor. When you're testing new medicine, how do you test out new medicine? Do you go out there and give it to everyone in the world to see if they get side effects from the medicine, from the medicine? No, we do not do that, right? Think about just inside this room here. How many of us have ever been part of a medical trial? I'd say very few or even none. Is there anyone who's ever been part of a medical trial here? I don't know if there's anyone, but I'd say very, very few of us have ever been part of a medical trial. But we use drugs that were actually tested. So how did they come to the conclusion that these drugs will not kill us if they give them to us? See? And that's where samples and population come in. They get a sample of the population, they perform some tests, and they decide to treat that sample as a representation of the population. So they do an analysis on a sample, and then tools from statistic, they basically tell us how much we can trust that sample. And we'll talk about some examples and we'll see different scenarios. Okay. So for our example, let's compare the 2022 World Cup and see how the sample compares to the full picture. Now, I think just dropping it in the chat, do you guys think the goal average for 2022 matches, was it higher or lower? What do you think? Just drop in the chat so that I know we're together. Do you think it was higher or lower? And there's no wrong answer or correct answer because it's not an analysis we've done already. Just asking. We've seen the overall average for the 92 years was 2.8, right? So do you think the average for just 2022, will it be higher or lower? What do you think? Anyone? And just drop it in the chat. As I've said, someone says lower. Okay, let's see. Lower. We've not done any analysis. We're just guessing to see who guesses something that's almost correct. So okay, let's do that. So the first thing we're going to do, let's look at the average again. Let's just get the average again, and we'll call that the population mean, right? So the population mean or average is equals to DF total goals, and we want to get the mean. So this is going to give us a population average. Just want to have them here together. Print population mean, and that's going to be population mean. Yep, like that. Let's use dot 2f like that. So the population mean is 2.8 that we'd seen we were expecting. So we now want to look at when FIFA decided to give Messi the World Cup, on a silver platter. How did the World Cup look that year? So let's see. We first need to filter our data set and get only 2022 results. Okay, so WC 2022 equals to DF. I'm just going to be filtering and we want to filter using the year, and we get only the ones that are equal to 2022. Let me World Cup 2022 dot head, just confirm. Yep, there it is. 2022 Qatar, Ecuador. That's a fair matches. Wait, 2022 started with Qatar and Ecuador. Okay, seems like I've also forgotten, but yeah, no worries. So we've managed to filter our data. We have the 2022 data. So let's look at the average for 2022 and see what it looks like. And for that, we can call it our sample mean. Sample mean equals to World Cup 2022. Again, total goals dot mean. Just want to print that. Um, 2022 World Cup mean was sample mean 2F. Yep, so the World Cup mean for 2022, the average was 2.69, slightly lower than the 2.82. Okay, so we've seen, I think, and an interesting thing, the difference between 2.82 and 2.69, very small, I think 0.13, right? So the means are close, but they are not identical, right? So the 22 average is within, I think it's almost the same. We can say it's almost the same. It's a very, very small difference, 0.13 goals. and it's not a bad sample. So we had 900 matches. We've taken a small sample, which is 64 matches. So 2022, there were 64 matches. We've taken that sample and we've looked at the mean for it. And the mean for it was 2.69. While it's not the exact same as the average, the population mean, it's a good representation by all means, right? We have like a very, very small difference, 0.13. And yeah, we've looked at one sample, but another thing to think about is, okay, what if we decide to do the average of every goals per year, like for every World Cup tournament? Let's just build what is it called, a bar graph that looks at the every goals that was scored for each World Cup. And we're going to just look at what was the average goals for all the different World Cups. And we'll see why this is important in just a few. And I think we're just trying to prove that yes, we can use sample means, but there are a couple of things, a couple of extra things that we should always think about. Just don't look at a sample mean and say, oh, this is good. One sample I've tested and it works and it's okay. So let's build a graph of the average goals for each year the World Cup was held. So how are we going to do that? We first need to group the goals by years. So goals by year equals to df, but group by, and we want to group by the year. And we want total goals dot mean. So we've created a new table that has the mean for each year. So goals by year dot head. So in the year 1930, the average was 3.88, 1934, 4.11, 1938, 4.66, 1954, 5.38. And we're already seeing something. So the population average was 2.8. The 2022 average was 2.69. So the average of 2022 is close to the average. But if we now decide to build like a whole graph, and already seeing something here, the earlier years, the average was a lot more higher. So let's see, we want to plot a whole graph, so figure, fig size, and let's go 12.5. And we're going to be building a bar graph, goals by year, dot index, goals by year, dot values, and color green. Let's just add some labels. So label is World Cup year. Label, the Y label is average goals per match. Let's just show. And look at that now. So average goals per match. In the early years of the World Cup, people were scoring a lot more goals compared in the second half of the entire time the World Cup has existed, right? So back to the question around, actually, let's also plot the population mean across this. Let's plot the population mean across it. So plot the horizontal line, population mean, color is red. So this is where the mean is. This is where the population mean is. But if you do a mean for every year, look at what we're seeing. In the early years, people are scoring a lot more goals. In the later years, less goals. So back to the question, and while we were looking at just France. When we looked at just France, and we saw that the average for 2022 was 2.68 kills, 2.86, 2 point, what is it? 2.69 goals. And our conclusion was that every sample mean is probably going to give us something close to the average. We would have been wrong. So when we're looking at samples, we've seen that the full population is telling different stories, and samples can actually mislead. So the 2022 sample told us it was 2.68. So it all comes down to the question that you're trying to answer. So if you are looking at just 2022, how did this perform relative to the average of the entire period? It would have been okay. But if we were trying to analyze the entire World Cup history and we use only the 2022 sample to draw conclusions, would have been very wrong. Because if we said, okay, we used the 2022 sample and we've seen that in 2022 the average goal was 2.68, and it means that for the entire period of the World Cup, goals were around there, 2, 3. It would have been only wrong. It would have been very, very wrong, because we've seen in the early years, people were scoring a lot more goals. The average was at around 5 points. I think, yeah, we had like 5 point something or almost 6. Yeah, it's 5 point something. We had 5 point something in the earlier years of the World Cup. Now, question someone might have, or a question I might also pose to you guys is, so I did talk about an example where I said doctors test on only one sample and then they decide to give us medicine. How are they sure that that one sample they've tested with is not a representation like of the entire population? What if the results are wrong, right? Because right now we've said if the question is analyze the entire World Cup history and we used only 2022, our sample would have been wrong to use for analysis of the entire World Cup history, because as much as it gave us something that's close to the current average, it's not a representation of how the World Cup has evolved. Because if we look at the averages for the entire history, we get to see that in the early years, people are scoring a lot more goals. And in current years, it seems like people are playing a lot more defensive football, because everything is 2.6, 2.6. The average is around 2 point something. People seem like people have been playing a lot of defensive football in the last couple of decades. So another question we get now is, so I did say doctors take one sample, they test drugs, and then they decide to give us these drugs. So how is it that doctors get to do that and we can't do something similar when you're analyzing our football data or something like that? Oh, see? So that's a question you'd have, or I'd ask. And how to think about it is, it depends with the question that you're trying to answer. What analysis are you trying to make? What are you looking for? So we're not going to say that the 2022 sample is wrong, but depending on the context of the question that you're trying to answer, it can mislead you, right? So if you decided, I want to look at the entire history of the 90 years the World Cup has been around, and then you pick a sample from 2022, 2000, 1998 events, all these samples are slightly around the same. They'd give you the same average, and they give you the wrong conclusion that the World Cup for 90 years, people have been playing defensive football. Whereas the reality is, in the earlier days of the World Cup, people were playing interesting football. People were trying to score goals. See? So, back to the question on the doctor. See, the thing with medicine is, if a doctor decides to test 200 patients from a population, and let's say these people are from only one country, they're testing only people they want to sell these drugs across the whole world, but they test with only people from America. Now, in that scenario, yes, their sample is going to mislead them, because They want to use these drugs on everyone around the world, but they're testing on a very, very small sample. So when it comes to sample, context matters a lot. What question are you trying to look at? What are you trying to analyze? And so on. So there are instances where your data set needs to be big enough for what you're testing, you see? So in our case, a data set of using only 1 year was probably not enough. We'd probably need to sample from different periods, maybe get something from the 1940s, get something from the 1960s, the 1980s, 2000s, 2010s, and so on, so that we can be able to create conclusions. See? If the doctor decides to use 200 people from one place, yes, as Sandra says, that sample is not a representation of the population. So it depends on the question that you're trying to answer. It's a very, very important nuance here. And in our case, the problem, when we looked at 2022, the problem is not that we used one sample. The problem is that one tournament, just 64 matches in one era, is too small, too narrow to answer a question about 92 years of World Cup history. See, if the question was, what was the 2022 World Cup like? Then that sample that we took is a perfect sample. It answers our questions completely. But if our question is, what does a typical World Cup match look like historical? For that question, picking only one sample, 2022, 64 matches, is not a good representation of the population of our data. We need a full picture. So the lesson here is that our sample always needs to match our question. A sample is only as good or bad relative to what it is that you're trying to find out. And that's why we said context matters when you're working with these samples. What are you trying to do? Okay. Once you have a concrete answer to what it is that you're trying to do, then you can figure out, okay, what samples to use, and so on and so on. Okay. So when we were doing this example where we looked at 2022, I wouldn't say we did anything wrong. I'd say we've not defined what exactly the question it is that we're looking at. Actually, our question is 2022 a fair picture of World Cup football? Actually, no, we did have a question, right? So is 2022 a fair picture of World Cup football? What's our conclusion now based on what we've seen? We looked at one sample and it gave us a certain result. But after looking at everything else, we realized, okay, 2022 is not a fair picture of World Cup football, like for the 92 years that it has existed, right? Because earlier on, games used to be very, very different. Yeah. Okay, nice. So I think takeaway here is samples. Most of the times, we will never use the entire population to perform analysis, or in real world, it's not feasible. We can't go testing drugs on everyone in the world. That's just one example we've used for. So we'll have to use samples. So it means it also comes down to how do you pick the correct sample? So you need to figure out what it is that you're trying to test for, or what question are you trying to solve or answer, and then it will guide you in making sure that you pick the correct samples, and then you can use samples, okay? So samples can be misleading if they're not chosen really well, but I think we now know what samples are, and we should be expecting to use them a little bit more. Now, another question we'll be moving on to is, do goals follow a certain pattern that we can use to do something? Like for the 93 years that we've had, do goals follow a certain pattern? And actually, I want to highlight something. I want you to look at most of the graphs. I think actually all the graphs, okay, we've done only 2 graphs, right? All the graphs we've done, they take a certain shape. I don't know if you've noticed that. They take a certain shape. Look at that shape. Same thing here. This one is a little bit tighter, but almost the same shape also. They take a certain shape. So, and that shape that we've been seeing, that histogram shape that we've been seeing, is actually a pattern, and it is very useful. So I'll be honest. So for our data, it's mostly leaning towards the right. It's not completely perfect. It's mostly leaning towards this is the right, this is the left. It's leaning towards No, it's leaning, this side is a bit higher compared to this side, but it's still a good sample. It's still a good data set to talk about this. And that shape that we've been seeing, it's called a normal distribution, and it's a pattern that is seen, I think, in almost everything in the world. If we go inside, if we're inside this room, we decide to check, I guess, maybe against everyone's edge, we probably get a similar shape, the bell shape. Yeah, it's bell shaped. We'll probably get a similar shape. Weights of fruit on a tree, from a tree, similar shape. So most values are going to cluster around the average, and the values become rare the further you go from the center. Okay, so that's what we saw here. You see, most values are clustering around the average here. The average is this red line, then most of the values are clustering around here and become smaller and smaller and smaller the farther away you go from the average. Do you see that? Smaller and smaller the farther away you go from the average. And that is called the normal distribution. And it's very, very useful. I think so. The thing that makes it like very, very useful is that it is defined by just two numbers, a mean and a standard deviation. And since it's defined by only those two numbers, it means there is a mathematical formula that can be used to describe a whole distribution. So if you have a data set and you have its mean and you have its standard deviation, you can draw that curve or that bell figure, and you can consequently use that to make let me not call them predictions, to calculate the probability of an outcome. See, we'll see an example, or we'll talk about that in just a second. So next, we're going to draw a few more graphs. Okay, so let's draw. So I'm going to draw, and I think I added this small note because I do plan to share this notebook with you guys later on. We're going to draw our histogram, and we're going to draw the curve using mean and standard deviation. So there is some maths behind how the curve is calculated and drawn. And I think I'm just trying to reassure you, don't worry about understanding every line for now. You can slowly try to figure that out. What matters is for us to show that our data follows that bell shape, you see? So for any data set, and you can go try this out later on, get a different data shape, try to do the same thing. Get its mean, get its value, draw a histogram, and when you compare, you'll see that you get the similar bell shape. So let's draw our histogram. So fixed size 10, 5. And then we now want to start by drawing a histogram. So total goals. So for beans, let's go. This is us defining how many columns we expect. 13, color equals to green. Let's give it a width of 0.8. And actual matches. Why are we labeling it actual matches? Well, because the whole point of this demo, next demo now, is to show that yes, if you have the data, you can generate that histogram, that graph. But even if you don't have the whole data and you have just the mean and the standard deviation, you can also generate a curve that follows that, a curve that is the same shape as your histogram. Okay, so this is why we label these actual matches. Okay, next thing is we now want to generate that curve. So x is equals to np. So for this, when you want to draw a curve, and I think let's go back to this. When you want to draw a curve, we want it to be a line, right? We want it to be a line. If we just decide to follow this, it will be like zigzags, cha, 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 and so on. So we want it to be a curve, like we need to have like several smaller like points along that we're going to follow so that it becomes like a smooth curve, okay? So we're going to create like 200 points that are going to make up our curve, and that's what we do here. So 0, 13, 200. And then we now define the actual bell curve now. So starts, it now, this is going to store the actual points that we're supposed to join together, the actual points that are supposed to join together to create the curve. So bell is equals to starts, and we're now going to use a function that we get from the statistics library that we imported a little bit earlier on. And what we say is mean goals, standard goals. Yep, like that. So what we do, and this is what I was saying, if you have the standard deviation and you have the mean of the data, you can actually create a curve using just that, and it would follow the same shape if you had decided to just create a histogram. So let's see how that looks like once you actually plot. So plot. So this time around, we're drawing the bell, and it's going to become a line. And for this, let's label it as the normal distribution curve. So what we've done is we've used this function for creating the normal distribution that we get from statistics, and then it gives us everything, and then we just come and plug it in here to Matplotlib to create a curve. And then I think let's show the legend. Hopefully there is no typo. Oh, I think we don't see it at all. Let me test here. We don't see the curve. Density equals true. Okay, I'll explain that. So we just use this key value to try and scale up our paragraphs so that they're on the same line as the curve. I think the curve did exist in what we had generated before, only that it was so big that it wasn't like we couldn't see it on our small canvas here. But when we say density is equals to true, it sort of scales down everything so that they are the same heights. Now look at this. So the one in the green, this is our histogram, and we've been drawing this like from the beginning. You see, that's the shape it takes. And the one in the red, this has been calculated mathematically using the mean and the standard deviation. Just that. And why is this important for us? Once we know, what is it called? Once we know this curve, or we can calculate, or shortly, once we're able to calculate this, we can now calculate probabilities using another mathematical function called the CDF, which stands for cumulative distributive function. Okay, so we're basically saying if you have a data set and you can get the mean from it and you can get the standard deviation from it, and you want to calculate probabilities of something, you can do that without having to go through all the 800 values or 900 values of your data, because we had 900 matches, right? 900 and something matches. So if I want to know, for example, what's the probability that, what probability is it that a match ended in less than 2 goals? Instead of me going inside my data, traveling across all those matches, checking, counting, this match ended with less than 2, less than 2, less than 2, less than 2. So once we have the data, we have the mean, we've managed to create the standard deviation, we can use mathematical functions to actually calculate probabilities. Now, something that we probably remember from, I think, was it primary school or from high school? Probabilities add up to 1, right? That's one thing that we need to remember. So the probability of something happening is or either zero is going to fall between 0 and 1. 0 in that not likely, 1 definitely likely, right? So it's going to fall between 0 and 1. So, for example, I think some better examples are, I didn't put them here. So an example now. Now we have this table. What is the probability? What is the probability that a match ends with 2 or fewer calls? So to do this, probability between A and B. So this is essentially between 0 and 2, right? Between ending with 0 goals or 2 goals. We just need to get the CDF of point B, CDF of point A, and we subtract the two. So this is what we do. For instance here, the probability of 2 or less goals, at the point where we have 2, you can just create a slice here. You create a slice here, create a line, and the area below the curve on this side where my cursor is, that is going to give you the probability of that scenario happening, okay? So, yep, the area under the bell curve between the 2 points is going to give you, subtract them and you get a slice. Yep, that's what gives the probability. So, now using mathematical functions, what is the probability that a match ends with 2 or fewer goals? So for that, probability of 2 or fewer equals 2. So again, we'll just get the CDF function from our library, norm CDF, and we say, and 2. We want to know whether a match can end with 2 or less goals, right? So 2 is our first point, and then we pass in our mean, and we pass in our standard deviation like that. And this is going to give us the probability of that happening. And it's F match with 2 or fewer goals. And that is going to be probability of 2 or fewer. Again, this is going to be in percent. It's a probability. Print. Why did I use printf? That's from C. So the probability of a match ending in 2 or fewer goals is 0.3. Now this is not percent, this is just a decimal, 0.3. If you want to convert this to percentage, yep, 33%. So this means in our data set, 33% of the matches probably ended with 2 or fewer goals. If you want to know maybe probability of a match ending between 2 and 4 goals, or what fraction of our matches end with between 2 and 4 goals. So this is where we now start doing the subtraction because we have 2 points between 2 and 4, right? When we had only just 2, we just needed this slice from this side, but now we want the slice between 2 and 4. So 2 gives us the slice from this side, 4 gives us the slide up to this point. So if we want to get between 2 and 4, we just need to subtract the slice of 2, okay? So for that, it simply becomes a simple subtraction. So probability of 2 to 4 equals to stats.norm.cdf. So we can start with 4 so that we can subtract mean goals, STD goals, minus stats.norm.cdf. And then we pass in 2 now, mean goals, standard deviation. Then we can now print and say matches with 2 to 4 goals, or what percent of our data set. So prob 2 to 4, right? 0.0%. And look at that. It now says matches with 2 to 4 goals or 39%. And finally, let's look at the other extreme, matches with more than 5 goals. So matches with more than 5 goals. So for matches with more than 5 goals, so probability of 5 plus goals equals to, now let's see how to calculate that. So 5 plus goals. So essentially we have a 0.5 and we need everything the other side. So the other quite important thing, remember we mentioned, is probability adds up to 1. So whatever we get after we calculate from the 0.5, 1 minus that is going to give us the remainder. So we're going to get, what is it called? We're going to get the remaining slice, because if we calculate for 5, we get this slice from here to here. But what we want is over 5, right? So 1 minus whatever it is that we get. So probability of 5 plus now is going to be 1 minus stats dot norm dot cdf, and I think it's 5. Then mean goals, std goals. Print matches with more than 5 goals. That would be probability of 5 plus. Yep, and matches with more than 5 goals, only 13%. So, yeah, so what we're trying to say here is from what is called, our data is always going to follow this pattern. We have a normal distribution curve. And this normal distribution curve, it allows us to do something extra with it. We can do something with this data, and which is we can get probabilities of something, right? So there is some mathematical functions that are involved. You don't have to build these yourself, CDF. I think I remember in computer science school, we had to learn how to build these out and everything. So the whole point of showing you this graph and this line is to show you that the curve exists, and this curve can be used to calculate probabilities of something happening based on the data set, right? So we have this data set, and we're saying, okay, matches with more than 5 goals, that was 13%. Matches with 2 to 4, that's 39. Matches with 2 or fewer, that's 33, and so on. And as you can see here, we did not have to perform actions on the data itself. I don't know if you guys are noticing that. We don't have to perform action on the data itself. We just had the mean, the standard deviation, and then the prediction that, the probability that we're trying to check for. So we're not going back to the data to try and like analyze it again, go through all the data to come up with these percentages that we've been working with here. Okay. Okay. So I want us to circle back to samples for a bit and talk about something else here also. So we've seen the World Cup has 900 plus matches, has had 900 plus matches in the 90 plus years it's been around. So what if you, as one person, let's say Asanda decides to has watched 30 of them. Maybe they've been alive that long, they've watched 30 of them, chosen randomly. They calculate average goals and form an opinion on that. Someone else watches a different sample of 30, and I think we all know they'll probably get a different slightly answer, right, on the average. Another person, another answer, and so on. So basically, all of us in this call, if we look at different samples, And if we look at different samples, we are going to get different averages. And I think we've seen a small representation of that out here, but just in here, it wasn't different samples, it was averages for different years, right? And we've seen that averages are going to be different. And especially now that we're introducing this scenario where everyone watches a different sample of 30 matches. So the question is, all of us have watched different samples, all of us have different averages. Which one of us is closer to the correct average? Or yeah, which one of us is closer to the truth? So let's sort of run that experiment together. So we're going to store the averages, so sample averages equals to, then for I in range 1000, we're going to run the experiment 1000 times. Each time we're going to pick 30 matches, and then we calculate their averages, and then we, what is it called? We store that in this list that we have here. So 30 matches equals to DF total goals sample 30. So we're getting 30 samples, and then for those, we now want to store the averages that we've got. So sample averages dot append 30 matches. Keep on having too many typos today. 30 matches dot mean. So we're running this experiment 30 times to see the different averages people are going to come up with. Let's see, we can just sample averages. March is incorrect. Why is it? Well, matches. Let's try to just print this out. I know it's going to be a very big list, hopefully not too big. Print. Yep. And look at that. I can see a 2.9 somewhere, a 3.3 somewhere, a 3.8 somewhere, a 2.7. In short, everyone is going to come up with a different average, right? 2.46 and so on. So let's just make this simple. So print lowest estimate. This is going to be, let's use a minimum. So mean of the sample averages. And let's limit the decimal points also. So that's lowest estimate from the, how many people? Is it 1,000 people? Yeah, from the 1,000, is it? Yeah, 1,000 people who watched. Highest estimate, here we go for max, and then true average is going to be DF, going to be DF total goals, close that dot mean. Look at that. So when 1,000 people each watch 30 random matches, the lowest, we've randomized this, the lowest got 1.87, highest estimate was 4.03, but the true average, the one that we know, was 2.82. So we're seeing that these, what is it called? we're going to get vastly different results. And the question is, okay, who is closest to the truth, right? You might be wondering that. So let's try to plot all of this. Let's just plot all of this. So plot dot figure big size 10, 5. Again, we'll plot a histogram of sample averages beans equals to 40 color and look at that. I think this is actually a more proper bell curve compared to what we've seen before, right? I want to plot dot draw. Yep, and look at that. We are seeing a better bell curve. Now, here's the most interesting thing that we're going to see today. Now, remember the true average is 2.8 goals. Now, interesting concept is that when you take like random samples of data, perform analysis on them, like the average, you calculate the averages for all of them, and you come and chart a graph for them, they are also going to be converging on the true average. So if I draw a line here of where the true average is, I think we remember the true average is 2.8, right? If you look at it, you'll see that 2.8 is going to be somewhere here. Okay, let's actually do that. So I will plot a vertical line, and it's for, no, I didn't store it for the mean. Okay, the total goals dot mean color equals to red, and anything else we need, a label. Let's call it true average. And look at that. Is okay, the label doesn't show. Can add a legend, plt.legend. Look at that. So the data is still converging on the true average. And this introduces us to a new concept, the central limit theorem. And it's basically, what is it called? Not that it says, the whole concept behind it is no matter what shape your data has, if you take many random samples and calculate the averages of each, those averages will always form a bell curve. And the center of that bell will land on the true population average. Okay. So, and I think it says that this is why statistics work. It works in the real world. You don't have to have a huge sample as long as it's enough. So you need to take maybe several samples, and your estimate will be closer to the truth, and you can calculate how close using something else called the standard error. And how do you get the standard error? The standard error is simply standard deviation divided by the square root of the sample size. So the smaller the standard error means your sample mean is more reliable. And a way to shrink this is to use a bigger sample. Now, earlier on, we talked about how when you're picking samples, we need to look at what question we're trying to answer, and it would guide us, right? How do you know the correct sample size to use? That might be a question you have. And that's where standard error comes in. How do I know a certain sample is correct for me to use? See, how do we know a certain sample is a lot more closer to the correct values that we're looking for? So in this scenario, 1,000 people watched an average of 30 matches. They watched 30 random matches, and they all created an average of the goals that they think, they created an average of the goals that were scored in the 30 matches. And you're wondering, who is closest to the truth? Well, there is a way to calculate that. Standard error. Remember, you have the standard deviation already. You have a sample size. You know it, right? You're the one who's coming up with the sample size. So to get a standard error, we've seen the standard error equals to df. We're getting the standard deviation. I think we have this in a variable somewhere at the top. I can't remember it. Divide by the square root of the sample size. So if our sample size was 30, and print standard error for 30 matches, is going to be plus or minus why is there not a complete? I forgot the F at the beginning. I'm wondering why things are not working. Standard error. Okay, so remember we said the smaller the standard error is, means your sample mean is a more reliable estimate. And the way to shrink that is to use a bigger sample. So let's say, for example, we decide to run, what is it called? We check for different sample sizes. So for n in a list. So let's check if the sample was 10, or 30, or 50, or 100, like that. So how do we know which samples are closer to the actual true average? We simply just check the standard error. The smaller it is, the better results we're going to get because it's going to be a better representation of our population. So standard error is equals to df total goals dot std divided by np dot square root divided by n, like that. Then we can now print and we say n is a matches, right? So n matches standard error equals plus or minus SE. That's the variable we've used here, SE colon, let's go 0.3F goals. Let's just create a small line. Something is broken. We forgot to close this. And look at that. Now look at this. So you said the smaller your standard error means the sample mean is a more reliable estimate. And an easy way to shrink it is to use a bigger sample. So look at this. If you have only 10 samples, your standard error is 0.609. So what does this mean? If you compare it with only itself, you can't get a reasonable conclusion. But if you compare it with maybe 30 matches, you get 0.352. So we see 30 matches is, what is it called? It has a smaller standard error compared to 10 matches. So 30 matches is probably a better sample because it gets you closer to the true average. If you go higher 50 matches, again, smaller. If you go higher 100 matches, again, smaller, and so on and so on. So this is probably one way to think about your samples as you're working with them. And I think we're running out of time. And we're down here. And the final thing we're going to look at is we're going to try and play around with the data, see if we can what is it called? We can use it on something real. And that's the upcoming match. I think, when is it? Is it tomorrow? Tomorrow, but one, the first match of the World Cup, Mexico and South Africa. And we want to see, is there any way we can sort of, I wouldn't use the word predict because as I said in the earlier on in the very beginning, it's very hard to predict. It's just a historical analysis. Yeah, it's a historical analysis. So we're just going to check how Mexico and South Africa have performed in all the World Cups they've played in, and see, is there a way, what is the probability of them doing a certain thing come this match that is coming up next week, in a couple of days. Now, we talked about the normal distribution here, and we said it's the bell curve that is available in almost all data sets, right? All data sets. And that's true. But it's not the only kind of distribution that exists. The reason for that is goals are discrete and they arrive in a specific way, randomly at a constant rate throughout the match. And each goal is independent of the last. Just because someone has scored a goal at the 10th minute doesn't mean that they will score goal at they'll score two goals at the 20th minute and so on, right? Each goal is independent of the last. So when events happen in a way that is random at a constant rate and independently, there's a different distribution that has been built exactly for that. And it's the Poisson, I think it's a French word, Poisson distribution or something like that. And it needs lambda, the average number of events, give it that, and it tells you the probability of 1, 2, 3, or so on events happening, okay? So this is not a prediction again. We can't possibly predict how the World Cup is going to end. And this is a good, I think it's a very, very hard task to perform. And this goes to inform you. See, those people that are claiming to they'll tell you how much which team will win so that you can give them money to bet for you. They're probably lying to you because it's a very, very hard task to predict how a match is going to end up. It's very, very unpredictable. But we have some data and we can still play around with it. Okay. So let's look at so from stats, want to import the Poisson. So let's start by looking at Mexico. So let's just, first thing, let's just create a data frame for only Mexico. So not for only Mexico. Let's just check the matches that Mexico played. So DF, where home team is equal to Mexico. Close that. Or DF, like, oh, I've forgotten DF, where away team is equal to Mexico. Let's see how many matches they've played in the World Cup. So you see, there's some simple analysis that we can do. Well, I wouldn't say we can predict anything. How many matches has Mexico played in the World Cup? I saw them in the very first World Cup. That's crazy. I think we were still being colonized back then. World Cup matches. So Mexico has been to 60 World Cup matches. I'm sure it's going to be less for South Africa. SA is equals to DF. Let me just copy this and change it to South Africa. South Africa, South Africa. South Africa. Yeah, and South Africa has been to only 9 World Cup matches. Now, this also goes to say we don't even have enough data to think, I don't know, I don't think we have enough data to try and say we can build a prediction. Mexico has played in 60 matches. That's over 90 years. South Africa has played in 9 World Cup matches. How many years is that? 9 times 4, around, oh, no, it's not. Sorry, I was doing that math wrong, incorrectly. Has played only 9 World Cup matches, and that's probably in recent years, probably after colonization stopped, unless I'm mistaken. Someone correct me if I'm wrong. I'm not sure when they started letting us play World Cups. But yeah, so we've seen already huge difference in the World Cup, the number of matches that were played. So Mexico goes to, so let's look at the number of goals that they've scored, combining both away and home. So this is DF, home team equals to Mexico. Then let's get the home score. I'm not getting autocomplete. I feel like I might have made a mistake there. DF, away team, Mexico, away score. There's a typo. Okay, I see it. Okay, so we've gotten their goals, and then now let's calculate the average of the goals that they, Mexico underscore average goes to Mexico goals. That mean I've not used it enough. So print Mexico averages, Mexico average. F goals per match. So Mexico averages 1.3 goals per match, but this is data that is for over 60 games, while South Africa averages how many per match? So I just need to switch to South Africa. South Africa. SA goals, SA average. Then finally, let's just print out SA averages, SA average goals per match. South Africa averages 1.22 goals per match, and they only played 9 matches. Okay, that's interesting. That's interesting. Okay, so yeah, as I was showing, we're going to get and what do you guys think based on this? This is showing that South Africa has an average of the average is more than Mexico. But are we feeling like they might score more goals than Mexico? highly unlikely. Mexico has their crazy goalkeeper. And as I was highlighting, our data not enough to make very, very, very useful conclusions. I think another thing we could check is, has Mexico played South Africa before? No, that's another thing we could check. Has Mexico ever played South Africa before? To see what that could look like. So let's just use the Poisson distribution to see what history suggests. What's the likeliness of Mexico scoring 0 goals or 1 goal or 2 goals or 3 goals or 4 goals and so on, okay, to see how that might look like. So we need to get lambda. So let's see, based on World Cup history. Print the probability of scoring exactly k goals. So if goals 6 or Mexico or expecting, why did I forget to close it here? Where else have I messed up? Closed here. Okay. So let's now, we're just trying to build out a simple table here. So print times 35. Yep, see, just building a very simple table so that we can see what is the probability that they score X goals for each country. So for K in range 5, so we're just going to build out from 5 goals. Mexico is equals to Poisson, PMF, K, Mexico, average. Let's go for South Africa, equals to Poisson, PMF, K, SA, average. And then we now want to print print let's see, max 7%. And then finally SA 12%. closing parentheses, don't match, closing parentheses, however I messed up, printf, okay. ISA12, again. So we have K string. If you guys see where I'm messing up, just let me know. Mexico, 7%, SA 12.1%, closing, or is it earlier? Print closes out at the end, right? Should have just used some simple print statements instead of trying to build a table. Okay, in range 5K, KK print. We have our opening parenthesis, closing parenthesis is here. F string. Do we close our F strings? Okay, here it is. Oh, yeah, and look at that. So based on World Cup history, likelihood of Mexico scoring 0 goals, 35%, 1, 36%, 2, 19%, 3, 6.5%, and so on. 4, 1.5%. South Africa, same thing, and so on. So as I said, this is not a prediction. Don't go and put all your money on Mexico winning or on South Africa winning. I don't think it's possible to do that with the data that we have, but we've seen that statistics gives us a lot of tools to analyze data that we have, and we can use it to base conclusions on this. And after you're done with the statistical process, which we said in the data science process, which is exploring, you can then now go and try to build models and then deploy models and perform action in those models. So I think that will be it for today. I know it's been a very long session, probably very confusing because there's a lot of, let me call it math that is used when it comes to statistics, because statistics is math. So take your time, try to learn some of these things, especially for you guys. I don't know, for data scientists, I think it's probably, okay, everything we've talked about is very useful for you to understand some of these things. For data analysts, because you want to analyze data, right? You can't analyze data when you don't know about all these patterns that might exist in data. And I wouldn't say I've even covered half of it. There is a lot more that's there to explore. There's things like confidence intervals, hypothesis testing, regression analysis, and from there it builds up to, what is it called? Machine learning and so on. So today was just an introduction, and I decided to just base it on how you might actually use the statistics tools that we get to learn this week to perform analysis of different kind of data. There's a lot of data out there. I'm sure you already know. Go check out Kaggle. You'll find data sets that you can use to perform actions, to analyze using everything that you get to learn this week. I think that will be it for today. This notebook will be shared later on. So let me just pass it on back to Halima. We'll close the call out for us. Over to you, Halima.
Alfred, thank you very much. Hi, everyone. I hope you guys had an amazing session learning statistics with Python. And I'm going to launch a poll now. Please kindly let us know your feedback. Okay, yeah. So there are just 4 questions. Please let us know what you think. Okay. All right. So as usual, if you have any issues, technical issues, maybe related to your assessments or learning content, you can ask the data programs team on eHub. There's a space for data programs team where you can ask questions. Also, you can drop a ticket on Fresh Desk, or you can reach out on Answer Base. All the links are actually on eHub in the space in this you on the all these spaces are actually on eHub space. When you just click on the program hub, you'll be able to see all the links like events and links to resources and links to Fresh Desk and Answer Base as well. So okay, next steps. Your assessment, this particular for this particular week, that's statistics with Python MCQ, will be due next Monday. That's 15th of June by 9:59 p.m. GMT. So let's endeavor to submit the assessment before then so that we get our 100% score. Otherwise, if you submit after the deadline, you all know that it will be capped at 50%. Also, the Python Basics Module Re-engagement Challenge, that's module transition, launched last week and is still currently ongoing. We only have 3 learning weeks left. That's this week, next week, and the one after. So now is a great time for you to catch up on any pending Python assessments, basic assessments that you have, so that you can strengthen your foundation and you can catch up on advanced Python topics as well. So as usual, if you have if you want to refer back to recordings for past PPL sessions and including this one, you find them on Program Hub space on eHub. And remember, as always, you're not alone in the community. You can always engage your squad mates, ask questions for clarity. You can post your wins and challenges and your new insights. And don't make it a solo movement. If you have something exciting that you want to share, you can always share with your squad members on your squad space. Or if you have issues or challenges, you can always reach out there as well. You can reach out to your technical mentors as well on eHub. Just type your technical mentors in. For example, you can type Alfred Tuva on eHub, or you can type Shegun Lawal, or you can type Lekun, just type your name on eHub, and then you can send him a DM. But it's strictly for technical issues, or if you have issues concerning learning, as far as Python learning is concerned. So don't make this a solo movement. Don't do this alone. If you are stuck, try to get unstuck, or try to get solution to your blockers, and don't just let it discourage you and just make you withdraw or make you just stop learning. Don't let it hinder your learning. Basically, there's always a solution for every challenge that you have. You just need to reach out to the right channel. All right. As of
Can we still
9 assessments.
Sorry.
Sorry?
I think either you dropped or it dropped on my side, but don't worry, you're back. We can hear you now. Sorry for that.
Oh, okay, okay. Oh, okay. You guys can hear me now. All right. Thanks, Alfred. Okay, I was saying that as of today, I don't know where you stopped hearing me from, but I was saying that as of today, you should have submitted 5 out of the 5 assessments so far. 5 assessments have been released so far. So you should have submitted 5 assessments already. And you need to pass at least 5 assessments out of all the assessments that are in the Python track for you to be able to transition to the next track, which is either machine learning or data engineering track that you choose. So please, for you to be able to transition, for you to be able to progress to the next track, you have to pass 7 assessments. So please, if you have any pending assessments, please kindly work on them so that you don't get left behind, and so that you can also transition. And if you have anybody that you think is lacking and you feel like you can help them, kindly reach out to them, pull them up actually, because that's what this particular challenge that is ongoing is about. If you have completed your assessments up to date, please reach out to people who you think are struggling. And if you see anybody struggling, kindly help them so that all of you can win together. You guys have been wonderful for showing up to this moment. You know, it's been really challenging, but you guys keep showing up for each of the PPL sessions. Shout out to Asanda, the likes of Asanda, the likes of I'm not sure I can get your names well, but you know, Asanda, Kitsi, Desmond, Anthony, Waweru. I'm not sure I'm getting your names. I'm sorry, guys. Benna, the chair, or I don't know. I'm really sorry. You guys have been showing up for PPL sessions and really appreciate it. Yeah. All right, that will be all for this week. See you all next week for next week PPL session. Bye, everyone.
It's the kids, baby.
Ooh, oh yeah, yeah, yeah. My chérie, my yo, my yo motola, my zinelele, my baby, my yo, my yo motola, my zinelele, baby. Zinibande gijwani malololo, we upo kwenye moyo kwa ndani malololo, hakuna matata, oh matata, ta, hakuna matata, oh matata, ta. Nekupenda nekutaka ni wewe tu, and I know. Nekupenda nekutaka ni wewe, so zinibande gijwani malololo, we upo kwenye moyo kwa ndani malololo, hakuna matata.